Hello, everyone, and thank you for joining the AstrumDrive podcast. Today, we're joined by Nelson, the head of our physics department. So, in today's session, we're going to do several things. So, the first is we're going to review our progress during Sprint 5. We're going to review what we plan to do in the next 2 weeks in Sprint 6, and also we're going to give a little bit insights of what we're currently doing. So, Nelson, please go ahead and give us a short overview about the progress we did in Sprint 5. It is currently on the screen.
Hello, everyone. Hello, Bailo. Thank you. Yes, we did several stuff during this last sprint. It was very interesting. Again, there are always interesting things happening when you work in the war drives. You find out new things. Well, what we did during the spring is basically we achieved to review in the starting review on the more important articles that we think are going and making good progress in the directions we want. These articles are the last year articles on Lens, for instance, and we have other articles for the next sprints, Bobrix et al. But in this case, we worked out uh, how Lens constructed positive energy or positive density energy solutions, uh, proposing a different approach to the type of observers you have. It is basically what he achieved was modifying a bit how the Eulerian observers, these Eulerian observers are the observers that are in free falling. And if you think about that, this is like the type of observer that can look at some the most easy understandable physics that you can get here probably, and he just made like I think it's a small contribution which has a great impact. He make it that this observers is defined in as a function in terms of some function. This function is you have like a derivative as a function, and this function obeys some wave equation. You expect this to have some sort of behavior like oscillating behavior or maybe decaying behavior. You can play with that. The point is like if you propose, he assumes that you have some wave functions, and with this wave function, then you solve this. There are several ways to solve it. He uses he basically finds the kernel, the green function associated with this solution, and he obtained a very nice shift vectors. And this shift vector is divided in three parts. Is the X, Y, and Z part. And basically, what he finally obtains by putting some conditions on this, or not, he didn't put the conditions. The conditions were there. He realized that there are some conditions there, and you see that you obtain an some energy condition, which is like a energy functions, which is depending of the density that you have, but also is also dependent of the a gradient of this density. And you have to integrate this because basically see all the contributions that you have in the space time. And you the interesting thing here is that under these circumstances, you can make this integration by following several paths of integrations, let's call it that way. And he realizes that what you obtain is that you can have positive defined solutions if you follow some specific past wave trajectories, which he combine get you a positive sign. This is basically what he obtains, and then he uses this. But this is like the major condition that you obtain here. Then you can propose under this condition any other significantly easy or complicated proposal that can follow this rule, let's call it that way, and obtain positive energy all the time. There are basically this is the main contribution I believe he did here, and then he worked out a bit about a proposal he has using some specific matter configuration, which is very interesting. He got very interesting results. Uh, we look into that because we wanted to know how for instance, how he approaches this problem of the how to modify the observer. So at the end of the day, it's the observer that you use, the observer that you propose is looking at the physics of the problem that is going to change the interpretation of the physics you have. Basically, that's the point. This is very complicated because one of the things is that in general relativity is all observer dependent in that sense. And then you have in these scenarios, you have observers that follow some type of geodesics and some observers that can follow other type of geodesics and time like or space like this changes the whole situation. You have quantities that are invariant under this, but uh, the physics that we're looking here is dependent of the server because we broke the covariance of the system by making this um, the constructions of the space times metrics, the same that Alcubierre did that everybody does in that way because that's the way. Then after that we check an interesting result that we found from the Santos and Pereira. These guys, what they did is they took that Cuvier metric and then, in a bit general way, they assume they have some function that is associated with the chief vector, and using this general function, they plug and obtain all the Einstein's field equations. Basically, you obtain a lot of equations, and then you start looking into these equations for all the scenarios that you have. Basically, what are these scenarios are? These scenarios are that you have derivative of this chief function that is left general but is included in Alcubierre, and this derivative can have some relationship between them. These are derivatives with respect to time, x, y, and z. So looking at these derivatives, they obtain a lot of cases, and they basically make that classification of cases, the possible scenarios that you can have. But we obtained something a bit different. What we obtained was that no, if you have the Einstein's equations, then these equations are coupled equations, which means that if you plug one equation into the other, so speaking, and then you can look into what is left after combining the equations, and you obtain that there are several things that are not uh, these are all mandatory things. You have restraints, you have constraints, and we found constraints in some of the derivatives. So we found that some of the derivatives, the first derivatives with respect, for instance, with y and x, these are zero, and it depends always which is the direction of motion that you assume. It changes which derivatives are zero, which are not. But the point is that we found some constraints, very specific constraints. This is very interesting because most of the work that you find concentrates on the fact that, yes, if you have dust in your system and you derive what is going on in the right hand side of Einstein's equation, which basically you get with only you get only the density energy, and the other hands you have the geometrical part, which is basically the extrinsic curvature and some combinations of it, and you obtain that these things tells you, yeah, it is the density energy is always negative. Well, that's true. That's completely right. What we found is that the constraints with the derivatives tells you that what you really find is like the geometrical side is always zero. So it's basically telling you that is a constraint that is always there about the density energy, which is new because basically it's telling you you're not violating the 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 weak energy condition. Basically, what you find is that you fulfill the energy condition, but it's not too interesting. Not very interesting. This scenario, but this is I think, and we think this is an important result because it tells you something about the metric you're using. It's telling you that this space times uh, can it's physical in a sense. So you have this constraint, and then you have to follow on this constraint and see what's going on. But on the other hand, if you just keep using these constraints, we found that this result shows that you fulfill weak energy condition, you fulfill null energy condition, and also the dominant energy conditions. And what we found is like the strong energy condition is the only one that has problems, which is okay because in fact Natarios proved in his article that this type of metrics either they violate the weak or the strong energy conditions. So it's okay. So we are violating strong energy conditions and we fulfill the weak energy conditions. So it's the result is very interesting because it's showing us that there is more that you can say, I think, about the what is it with this type of metric, because now we are studying I will get there classifications, more general classifications of classes of metrics like this one. One of all those also interesting thing is that we find out that there are some articles, and we use it, and one that I found very elegant to read is from 2010. It's from the Contour, and this article is concerning the energy conditions in the where you found likewise energy conditions in basically in quantum field theory and in general relativity. And these guys make a nice overview of everything here about these conditions, and you see that there is not a direct relation between the strong and the weak energy conditions. They basically what they tell you is they go both go tell bring you to the null energy conditions, which seems to be the most important one. But in fact, they say that there are no compelling physical arguments of why you should obey the strong energy conditions. So, in that sense, we are maybe there is a shortage in controversy in this direction, but we are more or less in a situation where we're following the physically uh, possible scenarios. It's very nice. We will
Nelson,
have this
Nelson,
this time.
let me comment this a little bit. Apologies for interrupting
Sure.
you. So it is widely believed that the warp drive is not physically possible. It's a mathematically elegant solution, which shows that this is like a certain possibility in certain universe, but not in our universe. So what you are telling me, my understanding is that uh, several things we thought are like impossible for the warp drive, they seems to be physical in our universe. For example, we can have local solutions which appear to be like with negative energy, but overall they're positive energy solutions. So you say that we thought that we cannot have like physical warp drive because of the zero or weak energy condition, but we found that this is also possible. And you didn't talk about that, but let's discuss a little bit about the horizon problem, that it was told that it's a problem which is going to prohibit the warp drive from happening. But actually, in our case, for the spherical metric for the warp drive, the horizon problem is perfectly fine. So it's not really a problem for us. So do you mind just talking about that a little bit?
Yeah, sure. I mean, what we have done, what I just said so far is just concerning Alcubierre's metric. In fact, this is not even dealing with our metric. These are results that are related to known metrics that have been studied from some time, which is amazing. I mean, basically what I'm saying is that you can have apparently this Alcubierre metric, this Alcubierre spacetimes, without needing this density energy there. There is no need of that. So this is
Negative energy or like energy density.
no density energy at all. I mean, while saying that we're finding this is zero, it's always zero.
I
It's
see.
not negative, it's not positive, it's zero. So this is already a result, which is, but this is physically possible in a sense, which is negative is impossible. So or at least as far as we know, positive is the ideal situation, and we found that is zero, at least as is state in this moment, this a specific metric. So what we are saying is that if we found this, which is something that apparently some other people skip or miss it, there is the possibility, there is a window there where we can look into positive solutions, not zero, positive that also have to obey these constraints that we found. And this is where basically we're working. And now into the spherical warp drives, that is our proposal, our first proposal that you just said correctly. In that proposal, let me go there then. We have instead of having this or cubiertos or natarios that you uses Cartesian coordinates, which is a very nice and very simple way to have uh, a mental view of this. We were using spherical coordinates and looking into a metric which is slightly different than the other metrics. And one of the things that we did is, yes, we checked the problem of the horizon. The problem of the horizon is there. I mean, it's always a problem that is concerning the fact that you are inside a bubble and you are in a flat space-time, which means that you are locally obeying all the physical laws that you need to obey. You have speed of light limits and so on. And then you have in the horizon something that is different. What is different? That if you have, for instance, some thin shell or you have some matter there, the point is that you have a type of curvature that the metric is telling you. And the problem is that if you send a signal from the inside, this signal is never going to reach this horizon. There is a problem. You're not ever going to reach it. It takes an infinite amount of time to get there. So it means that you are isolated from the outer space. So in a sense, the problem here is that you cannot control the chip from the inside. You have to control it from the outside. But that has several things there. I mean, we found that our spherical symmetric warp drive follows the same equation, but we now have to figure it out if there are some difference there that will appear later regarding the fact that we are using, I'm finding other constraints, different constraints, and see if some of those changes the situation. But the point is that we check it that we more or less have the same initial problems that everybody else has. But this is not really a big deal problem. It's something that you can face this problem later. First, if you have a positive solution, you already have a great results. And so we left this for the for consideration, later considerations. But it's quite nice because
So, uh,
concerning also, just go ahead, please. If you're going to ask me something.
for sure, I just wanted to make a comment that actually it makes a lot of intuitive sense that the warp bubbles are going to be as spheres, because the Alcubierre bubble is not exactly sphere. It's like contracting the space in front and expanding the space behind. And because the only like a bubble in space-time, like a, we can say warp bubble in space-time, we know exist are the black holes, and they, if they're not rotating or charged, they're perfect spheres. And also, I want to make a comment about the next thing that you said that the bubble has to be controlled from outside. And I just want to make a comment here. So we didn't talk about that yet, but we uncovered that when a warp bubble exists in space-time, most probably with the time it's going to disappear or dissolve. So if we find a way to control the bubble, the creation of the bubble, to sustain the bubble inside of the spaceship, in the moment we stop sustaining this bubble, it's going to dissolve it by itself.
Yeah, yeah. This is a very nice idea that we have. This is basically uh, uh, saying that if the war situation, there are a couple of comments that I want to do related to this. If you have the situation that is the bubble that is sustaining the warp effect, it means that as long as the bubble is there, you have a warp effect. If the bubble decays, then you lose the effect. So it's a way of saying stop, basically. And yes, it's a very nice idea. We're going to that, but yes, one step at a time. But this is we think that in that's a very nice way to approach the problem of the having no way of 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 controlling the situation from inside. And the other comment I want to make is that, well, in fact, Alcubierre's bubble, it is spherical. What all these guys have to different is that this expansion effect is quite different from other works. Alcubierre needs this expansion and contraction of the space-time, but other approaches, they already don't need this, which is very nice. It's more or less the first step that Notarios did. But at the end, you have a spherical situation all the time. Of course, you somehow break this sphericity once you choose a direction of motion, uh, and we're not doing that. That's the difference with us. We're not doing that. We said we have a radial direction, and we choose any radial directions is equivalent to us. But that's for us because we want to include more complicated matter configurations, which is leading me exactly to the next things that we do. We explicitly found perfect fluids configurations based on the work of Santos and Pereira, and starting to include, we found that we can use anisotropies, but we cannot use configurations that includes, for instance, heat. And we want to include almost everything we have, so we can give more complicated solutions, which also we expect to will give us more interesting results, and possibly to avoid or circumvent the problem of the negative energy situation.
And
Of
Nelson,
course,
sorry, I'm going to put another thought here. So we did a lot of research on the negative energy, so we didn't talk about that during the podcasts, but we think that we have a way to create it in a really smart way. And this is one of the reasons to include as many parameters in this equation as possible, especially the temperature. And I want to make another remark right now, based on our um, earliest comment about the dissolvement of the warp bubbles around the ship. Actually, this reminds me a lot about how the travel works in the science fiction, because you have like a jumps you're calculating, and if you want to go to a different place, you calculate another jump. So this is like an interesting analogy, because if we're able to control the bubble from inside, and this means that we can project a jump, the bubble is going to dissolve, and we have to make another one and another set of calculations every time we want to go to a different place.
yeah, it looks like that exactly. It looks like you need to have some jumps, and this is like a precisely like some science fiction approaches, which is you have to jump into pieces. This is very interesting. It looks very pretty much like that.
And Nelson, apologies for interrupting you, but just wanted to share these thoughts. I think it is going to be something interesting for the people listening to this podcast.
Yeah, sure. Yeah, sometimes it's too technical, but please ask us any questions or give us any ideas that you think. Um, yeah, but what basically that we found is that this spherical situation, we are studying, we studied perfect fluid with cosmological constant. Cosmological constant is something that you can include. It's really small, but you include it anyway because it might have some effect. It might have if much it is it can hit. This can be the difference between of having positive and negative density energy, just including cosmological constant. And this is part of the work that we already doing. Finally, what we check is what happens a bit. We check a bit what is the problem with causality, and we check out that basically causality problems are those problems that are concerning time travel. Uh, so if you have superluminal motion, you are allowed by the Einstein's equations to have some paradox concerning the possibility of time travel. But what we check is what are these problems? how people are dealing with this problem. This is an open problem by itself. It's not something that we can say, if you have some warp drive that is perfectly fine to use, it's going to solve the causality problems. No, the causality problems are going to be there, and there you have to solve it in some other direction. Basically, what I'm saying is that this is a part of the research. This research, it's not really into our scope at this moment, at least. But there are some hypotheses and that are going around in the literature, and you can read those. I recommend the work of Everett. This is a very old work, it's to 1996, and there are also other works about wormholes that Lobo, in fact, works on this, which is very interesting because he touches pretty much all the problems that you can have with this, and problems in the sense there are paradox, but it's not that the physics is not allowing you to do that. That's exactly the issue. Is we don't understand now. Nobody understands. Hawking proposes some hypothesis as the chronology protection, but this is just an hypothesis. It's not something that is proof. No. Anyway, we check that these are some problems that we might face. We wanted to have a clear view of the whole situation with the warp drives that we are uh, working very hard to understand.
So I want to comment a little bit the causality problem as well. So you're mentioning the Einstein equations, the field equations in general relativity. So to the best of my understanding, these equations deal how the matter behaves in space-time, but the warp drive itself, it is creating a bubble which travels through space-time, not inside of space-time. So maybe this is going to be a way for us to go around the causality problem because the causality problem it exists only in space-time. But if we appear and disappear in space-time, this means that we don't really travel superluminal in space-time. We travel superluminal through space-time. So this again like a part of our research, but this is like the approach we're currently having, that the causality problems are probably not going to be valid for us because we don't travel superluminal in space-time. The warp travels through space-time.
Yes, there are some concerns there, and this, in fact, this is well, part of the thing is that when these problems, Einstein's equations tells you when you have these extreme situations with space-time, and indeed, the equations tells how matter is going to move in space-time, but also tells how space-time is going to behave because the space-time is not fixed. The space-time is dynamic, is evolving, and it tells you how space-time is going to change because you have matter there. Both things are happening simultaneously. So, in that sense, is that's correct. I mean, we are like we have a bubble of space-time that is being created there, but also you have matter there. The matter is the matter that you're using, which is not the matter of the chip, is the matter
Bubble.
that you use to create the bubble. Yeah, and that's when it gets tricky, basically, which is telling you what, how is it moving, but the direction that you're pointing is exactly we want to clarify at least for our metrics and how this is going to work, how this is working, and see what happens. Maybe it's just allowed, you see, because there are with the models we have. I mean, general relativity have is very proof a lot of times, even recently. So we with the knowledge we have, there is nothing that tell us you cannot do this. So maybe it's allowed. And people call it problem. I'm mentioning like a problem of causality problem, but it's just a feature. It's not really a problem, and we will see uh, what is going on with that.
And also, it is going to be problematic from another standpoint to travel faster than light in space-time because you can easily hit a star. I mean, there are so many of them. So
Oh,
probably it's going to
that's
be
a
the
problem.
Yeah,
Yeah,
that
yeah,
is
yeah. But in fact, you can do that. I mean, if you have if you are thinking and traveling like matter moving to the speed of light or faster, that's
yeah,
not
so
possible.
at
This
this
is
point,
exactly what we're avoiding. Yeah, and yeah, yeah, there is a problem with colliding some astrophysical objects. It's a different problem.
right. So nice. Nelson, is there anything else you want to comment about the existing sprint before we move to the sprint planning for the next one?
No, I think that that's pretty much what we did during this last sprint.
Excellent.
Yeah.
It was quite effective sprint. We did some really good work. All right, so let's move to the sprint planning. Um, just give me a second. So we already put several things in progress. Do you mind just to give us a short overview about what we're currently planning to do?
Yes, well, this sprint is quite interesting. There are a few new things. I mean, we are, of course, still developing what we started during last sprint. Well, one of the most interesting things, one of the things, I'm still reviewing some of the new articles from last year. That's something that we are still doing. But the new things that I think the more interesting one is that is uh, we are now using the results that we found uh, with the perfect fluid and the cosmological constant from last spring, and these constraints we found with the Alcubierre's metric, and then we found different constraints with the spherical symmetric metric, our metric. Now we are working on putting the real consistent scenarios. The consistent scenarios, I mean, there are some consistency between you need between what is the matter content and what is the space-time content. And this is some very delicate situation. You have to be careful how to include the terms, how you have to think how to include terms. And this is when we want to include in this sprint heat. We know already that we are allowed to use to include anisotropies. So basically, this is very basically what we're working. And so the point is that we want to work on the consistency of the perfect fluid consistent with the Einstein's equation of the spherical symmetry and see which is the matter content that we can plug in. So basically, that's what we're doing in this sprint. And I can tell you already that this is a very this is really recent that we got an idea. This happens yesterday about how include heat probably into the systems, and hopefully in our next video I will tell you yes we did it.
Yeah,
And this is going to be very interesting. These are already new stuff that we are working on. And on the other hand, not so excited, but we're working on the Bobrik's article. And this article, which has is great, is that it makes a very nice classifications of the warp drive. They work very nicely on the geometrical part, and they make this classification. They have basically four classes, and they structure it in with different symmetries. In fact, they have this, the very first approach that I saw about spherical symmetry, but also they touch axial symmetry, which is like a, we can think it as a tooth or cylinder symmetry, and basically they make some ground foundations for we can use for constructing new metrics, and it's quite nice. And also, they clarify many technical points regarding the differential geometry that is around these objects that we are building. I mean, geometrical objects, geometrical spacetimes, and so on. And this is of course combined with what we are doing and putting new matter content and so on.
be quite interesting sprint. Do you have anything else to add, Nelson, about the upcoming sprint?
No, no, not really, not really. We are really working hard. We are trying to make as much progress as we can. Please let us know if you have any comment, anything. If it's technical, let us know, and we can try to put some less technical words during the next sprint reviews. And please support us. We're working very hard. We really want to have some very good results very fast.
Thank you very much, Nelson. And uh, many thanks to everyone who is listening this podcast. If you guys like it, please like it in YouTube, share it with friends. And if you feel like supporting us, you can do this on Patreon. We're sharing the link below. And with that, let me wish to all of you to have a very nice and successful week. Thank you for listening.